Welcome to the deep dive. Think about the devices you rely on every day, your phone, your computer. Inside, we're talking about microchips packed with hundreds of millions, even billions of tiny components. And these aren't just flat landscapes. They're intricate, layered structures.
Layers upon layers, stacked like microscopic cityscapes. And the fundamental challenge, making sure those incredibly thin layers stick together.
Right, reliably.
For years. Because if they decide to peel apart spontaneously, the entire device fails.
Yeah, disaster.
And this isn't just critical for microprocessors, but also for things like tiny mechanical systems, MEMS devices, optical components. Adhesion is everything.
And this challenge has actually grown as technology has advanced. A big pivot in integrated circuits happened when we moved from using aluminum wires or interconnects to copper.
That was a huge shift.
Copper's better for conductivity and speed, crucial for smaller, faster chips. But bringing in copper meant rethinking the whole material system, especially the insulating layers, the dielectrics between those wires. Now we need these things called low-K dielectrics. And getting copper to adhere reliably to them, or even the underlying silicon dioxide, introduces a whole new set of headaches.
Absolutely. It's not just swapping one metal for another. It's a complete material system redesign where interface integrity becomes paramount.
Right.
And those low-K materials, they're often less mechanically robust or might have different surface chemistries compared to older insulators, making the adhesion problem even trickier.
So that's our mission today. We've taken a deep dive into a fascinating doctoral thesis that zeroes in on this critical problem. Why thin films stick, or specifically why they don't stick, with a sharp focus on how their physical shape their geometry and how they deform their plasticity, play a much larger role than you might initially think.
This work provides a great roadmap through the complexities. We're going to unpack the core mechanism of failure, explore the ingenious ways scientists measure adhesion on this scale, dive deep into a particularly powerful testing method, examine specific materials like copper and aluminum, and uncover how factors like temperature can dramatically change the picture.
Let's start with the basics of why these thin films fail. It sounds like a simple peeling process, but what's actually happening?
Well, you can picture it as a crack that initiates and then grows along the interface between the thin film and the substrate it's sitting on.
Okay.
We call this delamination. And clearly, for device reliability, you need strong adhesion to prevent this crack from ever starting or growing.
Okay, so it's fundamentally a crack problem. But is all sticking power the same? I've heard there's a difference between the fundamental chemical bond and what actually matters in a real device.
There is, and it's a crucial distinction. There's the true work of adhesion, which is the energy required to break just the chemical or physical bonds right at the interface itself.
Assuming perfect materials.
Assuming perfectly rigid materials, exactly. You might get hints of this from idealized measurements.
So the pure molecular attraction.
Pretty much. But in the real world, especially with materials that can bend, stretch, or deform like metals when that crack starts to grow, a significant amount of energy isn't used to break the bonds. It's dissipated by the material deforming plastically near the tip of the crack. Think of it like the difference between shattering a brittle ceramic tile versus trying to pull apart two pieces of chewing gum stuck together.
Oh, okay.
The chewing gum stretches and absorbs a lot of energy before separating.
So the practical adhesion is that bond-breaking energy plus the energy soaked up by the material deforming.
Precisely. And for ductile thin films like copper, that plastic deformation energy can be enormous compared to the energy needed just to break the interface bonds.
Wow.
So it's the practical work of adhesion that we often need to measure and understand for designing reliable devices.
And understanding these cracks involves fracture mechanics concepts, right? Like the energy pushing the crack versus the material fighting back.
That's the framework, Fracture mechanics describes the energy available to make a crack grow. That's often called the strain energy release rate, G. And the material's resistance to that growth is its toughness, sometimes called O or WAP, aligning with that practical work of adhesion.
Got it.
And cracks can grow in different ways depending on how the force is applied. Pure opening, mode 1, pure sliding shear, mode 2, or tearing, mode 3.
And for interfaces between different materials, it's not usually just one of those modes.
Rarely, if ever. Because the materials are different, you almost always have a mix of shear and normal stress at the crack tip. This mode mixity is described by a phase angle, usually called psi.
Size, okay.
And what's really interesting and complicates things enormously is that the toughness of the interface, how hard it is to break, depends strongly on this mix of stresses, on this phase angle.
So how you try to peel it matters immensely.
Absolutely. An interface might be tough under pure pulling, but weak if there's a lot of shear.
Right. And how the film itself behaves matters too. Brittle versus ductile.
Definitely. Whether it snaps like a brittle material or stretches like a ductile one depends on its yield strength, how easily it starts to deform permanently, and the intrinsic bond strength.
Right.
If the film has a low yield strength and the intrinsic interface is pretty strong, the film will deform extensively before the interface breaks, dissipating lots of energy and boosting that practical toughness.
So making the film softer almost could help.
It suggests that, yeah. Or introducing a thin layer that promotes deformation might actually improve practical adhesion.
Okay, so we've got the theoretical backdrop. But how on earth do you measure this practical adhesion for layers that are literally only a few nanometers or micrometers thick? It seems impossible.
Well, that's where the experimental ingenuity comes in. Over the years, researchers have developed a whole toolkit of tests.
Like what?
There are tests using the internal stress already present in the film, like the superlayer test. There are indentation tests, where you push a tiny tip into the surface. Scratch tests, where you drag a tip. Bulge or blister tests, where you apply pressure from underneath. And tests using larger sandwich samples where the thin film is embedded.
A lot of options. But I gather many of these has significant drawbacks, especially for the types of films used in chips today. Thin, ductile metals, like copper.
Exactly.
Measured exactly as they are processed, without altering them.
That's a major hurdle. Many standard tests aren't suitable. Some are just incredibly time-consuming. Others can only apply a limited range of stress states, meaning you can't probe that critical dependence on mode mixity.
Right, that phase angle thing.
Yeah. A big issue is that with ductile films, many tests cause the film itself to deform plastically before the interface actually breaks.
So you're measuring the wrong thing.
Kind of. It makes it hard to measure the interface strength specifically, and some methods require high-temperature sample preparation that can fundamentally change the interface you're trying to study.
Which means you're not measuring the adhesion that matters in the final device.
Exactly. So there's a real need for a test that can apply a wide range of stress states, account for the residual stresses already in the film from processing, and handle ductile films without changing their properties or getting dominated by the film's bulk deformation.
Okay, and this is where the thesis focuses on a particular method, the superlayer indentation test. Tell me, what makes this one so effective for these challenges?
This test is quite powerful because it addresses many of those limitations. The core idea is this. You deposit a second, much thicker and harder layer, called a superlayer, on top of the thin film you want to test.
A superlayer.
Yeah, often tungsten or something similar. This superlayer is often deposited with a significant internal stress, like compressive stress, which adds energy to the system.
So you're putting the whole stack under stress to begin with?
Partially, yes. The superlayer's internal stress is key. But because it's hard and thick, it also acts like a rigid lid.
Okay.
When you push down with an indenter tip, this rigid superlayer helps constrain the underlying thin film, preventing it from just pushing out of the way or piling up excessively.
I see. It holds it down.
Exactly. This forces the deformation and failure to happen more specifically at the interface underneath.
Okay, so you build this three-layer stack, substrate, your thin film, then the stressed, rigid superlayer. What happens when you push?
You use a sharp, controlled indenter tip, similar to what's used for measuring hardness, like a Berkovich tip. As the tip presses into the stack, the stresses build up, and eventually, the thin film debonds from the substrate around the indent, forming a circular blister.
You push down in the middle and it peels outwards in a circle.
Exactly. And by carefully measuring a few things, the mechanical properties of your films, like their stiffness and hardness, the geometry of your indenter tip, how deep you pushed the indenter, often precisely measured using techniques like the Oliver Farr method, which analyzes the load and depth during the test, and crucially, the diameter of that debonded blister using microscopy, you have the data needed.
And from that, you can calculate G, the practical work of adhesion.
That's the goal. One of the biggest strengths of this test is its ability to create and measure adhesion over a wide range of phase angles, that critical mode mixity.
Okay.
As the blister grows, the stress state at the crack tip can change. And this test can capture how the practical toughness changes with that mode mixity. You can even see things like R-curve behavior, where the resistance to cracking changes as the crack gets longer.
So it's quite sophisticated.
It is, and we can see visually how important the superlayer is. Images often show messy deformation without it, versus a clean, defined blister when the superlayer is used. The stress and thickness of that superlayer are engineered to ensure there's enough energy available to drive the crack at the interface.
Okay, that makes the method clear. Let's apply it to the specific materials in the thesis, starting with copper. What did they discover about copper film adhesion, particularly on silicon dioxide, a common material in chips?
Right, copper is the workhorse now in integrated circuits, replacing aluminum because it's more conductive and resistant to electromigration.
Which causes failures.
Exactly, especially in tight spaces. But as we touched on, getting copper to stick reliably, especially to insulators like silicon dioxide or those newer low-K materials, is a known challenge. Copper can diffuse, it doesn't always bond well chemically.
How were the samples prepared for the copper study in this work?
They used copper films deposited by sputtering onto silicon dioxide substrates. Some samples had just copper directly on the SiO2.
Okay.
Others had a very thin, just 10 nanometers layer of titanium deposited first as an underlayer between the SiO2 and the copper.
A tying underlayer.
Then a thick 1.1 micrometer tungsten superlayer was sputtered on top of everything. And the sputtering process leaves residual stresses in the films, typically tensile in the copper and compressive in that thick tungsten layer.
Got it. Substrate, maybe a thin titanium helper, the copy layer, and then the heavy, stressed tungsten lid. What did the test show about how copper adhesion changed depending on how thick the copper film was?
For the copper films directly on SiO2, they found that the practical adhesion, the G value, generally increased significantly with film thickness.
Okay. But really only for films thicker than about 100 nanometers. For very thin films, it seemed to level off at a lower value, around 0.6 joules per square meter.
0.6 JM2, that sounds tiny.
It is, relatively speaking. That jump in toughness for thicker films is a strong indicator that something beyond just the interface bond is dominating, that it's the energy absorbed by the copper deforming plastically near the crack tip.
So the thicker the film, the more crumple zone there is to soak up energy.
That's a good way to think about it, yeah. Calculations of the plastic zone size near the crack tip confirm this. The size of that deformed region scales with the toughness and the film's yield strength. For the thickest copper film tested, 3 micrometers, the calculation suggested the plastic zone extended through the entire film thickness.
The whole film.
The whole film. And this correlated with a massive measured G value, over 100 JM2.
Whoa.
Indicating huge amounts of energy being dissipated through that full film plasticity. Wow, from 0.6 to over 100 J-meter-2, just by changing the thickness and enabling that full plasticity. That's incredible. What about that thin titanium underlayer? How did that affect the picture?
The samples with the 10-millimeter titanium layer showed some interesting results. Analysis suggested the titanium likely became partially oxidized during processing.
Okay, so maybe titanium oxide there.
Possibly. And when these films delaminated, the fracture path consistently ran along the titanium-copper interface, not between the SO2 and the titanium.
Ah, so the tie stuck to the SiO2 just fine?
Apparently. And notably, the adhesion values, the G values, were generally higher with the titanium underlayer, again, especially for thicker copper films.
That's counterintuitive. A separate layer and a thin, possibly oxidized one at that, actually improved the practical adhesion, even though the break was happening right at its boundary with the copper. Why would it help?
This is where the plasticity insight is key again. The analysis suggested the titanium didn't necessarily make the interface chemically stronger or even change the mode mixity much. The phase angle estimates were slightly lower with the titanium.
So it wasn't a better bond or a better stress state?
Doesn't seem like it. Instead, calculations indicated the plastic zone size near the crack tip was larger in the copper films with the titanium layer compared to those without. The titanium layer seems to somehow facilitate more extensive plastic deformation in the adjacent copper film during crack growth. So it's promoting more energy dissipation in the copper.
I see.
And that's why the overall practical adhesion goes up, even if the new interface is where the failure happens. It changes how the system dissipates energy.
Fascinating. It's not about making the bond unbreakable. It's about making the failure absorb maximum energy. Okay, what about another variable, temperature? Did they test adhesion at different temperatures?
Yes, and this yielded one of the most dramatic findings. They tested copper films from room temperature, 23 degrees C, up to 130 degrees C.
So not extreme temperatures, but warm.
Right, relevant for device operation. The practical adhesion, the G value, showed an absolutely massive increase, more than an order of magnitude jump as the temperature rose.
An order of magnitude? Yeah. Just by going up to 130 degrees Celsius? That's a huge effect.
It is a really significant change, and the reason ties directly back to the material's properties.
Okay.
Nano-indentation tests confirm that as the temperature increases, the yield stress of the copper film decreases significantly, becomes softer, more ductile, easier to deform plastically.
Okay, makes sense. Metals get softer when hot.
Exactly. A lower yield stress means that for a given stress level at the crack tip, the copper can undergo much more plastic deformation.
Right.
And as we discussed, that increased plasticity is the primary mechanism for dissipating energy and increasing the practical work of adhesion.
So the higher temperature makes the copper film act more like that chewing gum soaking up energy, rather than the interface bonds fundamentally changing.
That's the strong conclusion from the thesis. The temperature dependence of adhesion seems dominated by the temperature dependence of the copper film's yield strength and its resulting plasticity.
All right, so we've established that plasticity is a dominant factor, influenced by thickness, helper layers like T, and temperature. What other insights did they gain about what's happening right at that tiny crack tip, or how the failure process unfolds?
Well, the thesis also looked at theoretical models, like the dislocation free zone model, or DFZ.
Okay, sounds complicated.
It is a bit, but these models try to connect the microscopic behavior specifically, how dislocations, which are line defects that enable plastic deformation in metals.
Right, the things that let metal bend.
Exactly. How those dislocations behave near a crack tip to the macroscopic toughness we measure, while there's always some variation, some scatter in the data.
Sure.
These models provide a theoretical framework that supports the experimental findings about the link between yield stress and toughness, especially explaining that big temperature effect.
So the atomic level theory aligns with the bulk measurements. Were there other ways they listened to the process?
Yes, they used acoustic emission, or AE. This involves using sensitive sensors to detect the tiny sound waves or stress pulses generated by discrete events within the material as it deforms or fractures.
Like listening for pops or clicks as the interface breaks or the film buckles.
Precisely. They found that these AE signals correlated well with events observed during the indentation process, like sudden load drops, which are often associated with buckling or cracking.
Interesting.
And samples with the titanium underlayer, which showed higher measured G values due to enhanced plasticity, also generally produced higher energy AE signals.
So more plastic deformation, more noise.
It suggests that, yes, this implies AE could be a useful comparative tool. If one sample makes more noise during the test, it might indicate more energy is being dissipated, implying higher practical adhesion, at least relatively.
That's a clever way to get indirect information.
Yeah.
And after the test, they could examine the crime scene with microscopes. What did they see?
Absolutely. Optical microscopy, scanning electron microscopy, SEM, and atomic force microscopy, AFM, were used to look closely at the surfaces after the test. This helped confirm where the fracture occurred and reveal details about the failure process.
And the AES analysis confirmed the break location, like you mentioned?
Yes. Auger electron spectroscopy, which is very sensitive to the elements present on the few atomic layers of a surface, was used.
Right.
For the copper-only films on SaO2, the failure surface was dominated by silicon and oxygen, confirming the crack ran primarily at the copper-SiO2 interface.
Okay.
Though, with hints of it, sometimes pulling a bit of copper with it, what's called cohesive failure within the copper near the interface.
A little messy sometimes.
A little. For the copper on titanium samples, the analysis clearly showed titanium and oxygen on the fracture surface, confirming the failure consistently occurred along the titanium-copper interface, making that the system's weakest link for fracture propagation.
Okay, confirming that the titanium layer shifted the weak point, but in a way that made the overall system tougher due to plasticity. Were there any unexpected features on the fracture surfaces?
They observed some fascinating details. There were distinct circular fiducial marks.
Fiducial marks.
Yeah, like reference marks. They corresponded precisely to the maximum size of the blister just before it might have propagated very quickly or unstably.
Ah, so it shows where the crack front was at a specific moment.
Exactly. These marks essentially outline the crack front during unstable growth and provide clues about the crack dynamics. They also found some unique petal-shaped marks near the center of some blisters.
Yeah, petal-shaped.
Yeah, the origin wasn't fully clear, but might relate to how lubricant used on the indenter tip or even trapped water vapor is extruded from the interface during the high-pressure indentation.
Like imprints left by something getting squeezed out. Weird.
Possibly. And sometimes, particularly with materials that adhered very well or were very ductile, the test didn't produce a clean delamination blister at all.
What happened then?
Instead, the indenter just caused significant plastic deformation in the film and superlayer, what they call plastic pileup.
Just squished it.
Basically. This is important. It shows the test measures the weakest link. If the interface is incredibly strong or the film is so ductile it deforms endlessly under the load. The test effectively tells you that the film's yield strength is reached before the interface fails, making it hard to calculate a traditional G value for the interface itself in that specific test.
So if it just squishes the material rather than peeling it, the interface is stronger than the film's ability to deform under those conditions.
That's one way to interpret it, or that the energy required for massive plastic deformation exceeds the energy needed to break the interface within the constraints of the test setup.
You mentioned aluminum earlier as the predecessor to copper.
Yeah.
How did its adhesion behavior compare in these kinds of tests?
Comparing with aluminum is valuable context, yeah, because it was the standard for so long. Aluminum actually has naturally good adhesion to silicon dioxide.
Oh, really? Why is that?
It tends to form stable aluminum oxide layers right at the interface that create strong chemical bonds with the silicon dioxide.
So inherently good sticking to SiO2. What did the tests show when they used this superlayer method?
They tested aluminum films with tungsten superlayers using the same indentation method. Similar to copper, they found that the measured practical adhesion, the G values, increased with aluminum film thickness.
Okay, so plasticity matters for aluminum too.
Definitely. Again, evidence that plasticity plays a significant role in the practical toughness of ductile aluminum films.
And did the superlayer stress matter, like with copper? Did compressive stress help?
Yes. They showed that using a tungsten superlayer deposited with a compressive residual stress resulted in higher measured G values for aluminum films compared to using one with a tensile stress.
Consistent.
Exactly. It aligns perfectly with the theoretical understanding of how the energy stored in the film superlayer stack contributes to the energy available to drive the crack.
Okay, similar plastic behavior and sensitivity for residual stress.
Right.
But what about contamination effects with aluminum? You said it sticks well naturally, but what if something gets in the way?
They did look at that, and this provided a really stark contrast to aluminum's naturally good adhesion. They deposited very thin, just 40 nanometer layers of either copper or carbon before depositing the aluminum film on the SiO2.
Just 40 nanometers, tiny.
Tiny. And this had a dramatic negative effect. It significantly reduced the aluminum adhesion. The G values were much, much lower than for the uncontaminated aluminum films on SiO2.
So a tiny layer of contamination, just 40 nanometers, and aluminum's good native adhesion basically disappeared.
Precisely.
Yeah.
It powerfully illustrates how incredibly sensitive thin film adhesion can be to interface chemistry and the presence of weak interlayers, even seemingly minor ones.
Wow.
Interestingly, for the aluminum films on the carbon underlayer, the thicker aluminum films actually showed slightly lower adhesion values.
Lower. That's weird.
Yeah, which was a bit unusual and highlights the complex interplay of factors like residual stress contributions in specific material stacks. But the main point was the devastating impact of the contamination layer itself.
So cleanliness is absolutely paramount then, down to the nanoscale.
Critically important, yeah. Seems like even very thin layers can ruin things.
All right, we've journeyed from the core problem of layers not sticking to the sophisticated measurement techniques, delved into the specifics of copper and aluminum behavior, plasticity, temperature, and even peered into the microscopic details of failure. So, stepping back, what does all of this deep diving into a doctoral thesis mean for you, the listener, who relies on these technologies every day?
Well, it means that the invisible world inside your devices is governed by incredibly complex material science. Understanding why and how these thin layers stick together, or fail to, isn't just academic curiosity.
Right, the entire device depends on it working.
Exactly. This understanding is fundamental to designing and manufacturing reliable microelectronic devices, sensors, and other systems that use thin films. By knowing that things like film thickness, temperature, and even tiny interlayers dramatically affect adhesion by influencing plasticity, engineers can design better material stacks and processing methods. They can choose materials or add layers specifically to manage that plastic deformation energy.
So this knowledge helps prevent failures, allows devices to last longer, and ultimately enables continued progress in making things smaller, faster, and more powerful. Without solving these adhesion puzzles, that miniaturization literally wouldn't be possible.
That's the real-world impact, absolutely. The key takeaways are clear. Measuring thin film adhesion is tricky and requires specialized tests like this superlayer indentation method.
Right.
For ductile metals like copper and aluminum, practical adhesion is often dominated by how much energy the film can absorb through plastic deformation at the crack tip.
The crumple zone effect.
Yeah, exactly.
Okay.
Often much more than just the strength of the initial chemical bond. Factors like film thickness and temperature have a huge impact because they change how easily the film deforms.
Okay.
Even thin interlayers can significantly alter adhesion, sometimes beneficially like the titanium by promoting plasticity, but interface contamination, even a thin layer, can be catastrophic for adhesion.
I'm finally in this again.
Yes. And we need all the tools modeling, acoustic emission, microscopy, to really piece together the puzzle of the failure process.
It's truly a delicate balance of materials, science, and mechanics, all happening on an incredibly small scale.
It is, and a complex one. Lots of interacting factors.
So here's a final thought to leave you with. Despite the incredible insights gained from work like this thesis, fully predicting and controlling thin film adhesion across every possible combination of materials and processing conditions remains a grand challenge.
Oh, definitely.
We've seen how engineering the film's mechanical behavior, its plasticity, is as important, maybe sometimes more important, than the interface chemistry itself.
This raises an important question. What if we could simultaneously engineer both the interface bonding and the film's ability to deform at the crack tip with atomic precision?
Controlling both the glue and the stretchiness perfectly.
Something like that. What would the ultimate limit of adhesion between dissimilar materials look like then, and what entirely new technologies could that level of control unlock? Think beyond electronics, maybe even to biological interfaces. It's a fascinating frontier.